We have Jakub Szut is an assistant and PhD candidate at AGH University in Krakow, Poland. Is senior software developer at Ericsson, and he researches RF energy harvesting, working on transmitterless solutions that can operate in ambient energy from civil infrastructure. So please give a warm welcome to Jakub.
Okay, thanks a lot. I think I'm observing it from yesterday. I think that Seth's introductions are really underappreciated. So he's doing great job with those introductions. So just to mention that. So hi everybody. Thank you for the invitation, the possibility to speak. This will be a little bit different presentation that all the others stuff where presenters were talking about commercial uses mostly or hobbyist approach. But I want to present you how KiCad can be used in sometimes a little bit dull, but not mention but academic approach and research. Generally speaking, now a little bit of introduction to what I am working around with, and please stop me if I will start the second hour of introduction because I can talk it endlessly, but I will try to be quite short with that. So generally, RF ambient energy. We live in Europe, we all know that we need to look for new sources of energy. Power grids are of course important, but we tend to look for sources that are more eco-friendly, cheaper, but first of all available. So this first step was those all renewable energy sources like solar energy and wind and water, for example. But with the development of electronic devices and the trend of creating smaller and smaller chips, we find out that we need much less energy than previously. And then we started to look into the idea originally proposed by Nikola Tesla over 100 years ago. So he had a dream to transfer the energy wirelessly. His assumptions were a little bit wrong when it takes to our current understanding of physics. But in fact, we can a little bit make his dream come true and share the energy wirelessly. Shortly, generally, all of your phones receive data from BTS or in 5G GNODBs. So you get this information, but to get this information, it needs to be transferred. And to be transferred, there is a need for some kind of energy to be emitted to create the path between you and the transmitter. And this energy, after the data reaches your phone, is dissipated. It's lost in the environment. But as I mentioned, in days where we need not watts, single watts of energy, but microwatts to power up. For example, there is, I believe, A0 Cortex that requires around 5 microwatts per core to operate basic things. We can try to get this energy, and there are a few approaches to do so. So first of all, the commercially already available sources. So for example, PowerCast, which uses transmitter, which is okay, it works, but you generate additional RF emission around you, so maybe not so good idea. Anticipated energy sources, so communication architecture mostly, so routers, BTSs, and other communication stuff, and also this ambient one, like let's say emergency resources for direct communications, which are quite unpredictable. So we are not very interested in them. So, okay, after this maybe a little bit too long introduction to the RF energy, let's go further and getting closer to KiCad. I promise you, in a few slides we'll get there. But generally, to get there, I want to show you a little bit what is used to get this energy. So this is called RF energy harvester. And this is a special circuit that consists of receiving antenna with a few stages after that. So depending on the design, you can have impedance matching network, rectifier, voltage multiplier, power management, and applications. Generally, receiving antenna is something you can compare to the power source. Later on, you need this power to be a little bit fitted to the rest of your circuit, and then you can rectify it to get DC for your further use in the circuitry. And here comes the research that we recently started. So the rectifiers and the stage between receiving the power on the antenna and getting into the rectifier. And here comes our problem. It's quite costly to produce every single possible configuration of the design for RF energy harvesters. It's high frequency circuit that has a few components that has to be optimized to operate properly. And this is why we started to look for some kind of workaround for our issue of comparing results of different topologies, architectures, and we get to simulations. So of course, apart from the prototyping cost, even the measurement of such circuitry is quite difficult because you need both high-frequency generators and spectrum analyzers, which is way over the budget of a regular academic research project, unfortunately, still. But what is also important that I believe the difference in the atmosphere here and outside of the building will effectively differ in the results that we'll get when trying to measure it here. So special labs, EMI and EMC chambers should be generally used to conduct such measurements. This is why, once again, simulations seems to be quite a good idea, because we can have those conditions under control. And of course, what I've stated at the beginning, there are a lot of architectures and topologies, and in one moment we'll need to tune parameters, so it's easier to do in simulation rather than on real stuff. The first thing that we notice is that for example, Schottky diodes, which are, let's say, the basic approach to create a RF energy harvester, there are provided SPICE models of such high-frequency diodes. Interesting facts, when you dive into the academic papers in this topic, you will find that around 80% of papers published use this particular Schottky diode, HSMS 2850 or 5, depending on the packaging. The problem is it's no longer produced for around 5 years. So I don't know from where they got those diodes, but hopefully they got there rather than publish on outdated models. But, well, still, SPICE models are there. We can use them to the simulation. But that's not, let's say, the whole solution of our simulation environment. We also need somehow to simulate the receiving antenna. So maybe you remember from school or whatever, Thevenin's theorem, simply any source of voltage of power can be replaced by a simply you have to get the output similarly. It just, a rephrasing of this theorem, but simply, as you can see, if you want to simulate antenna, you need the alternating current source with some kind of comparable resistance, and for antennas it's very often 50 ohms. And this is how we get the antenna simulated. And here's also the first part that we use KiCad for. Of course, we also need to calculate proper amplitude, but it's quite a few easy operations to be done. And then we started to think last year, what particular environment should we use? There are a few of them, including KiCad and ngSpice included in it, but there is also LTSpice, pSpice, and so on and so on. And there is widely used in academic research MATLAB, Simscape Electrical. Of course, it's used in academic research, but it's also very pricey thing. So we started to wonder if it's really better than all other solutions available, or it's simply preferred by academics due to their habits. So we started our research with comparing those three, let's say, most popular tools. This is our circuit provided in Simscape Electrical. For me, it's not super, let's say, easy to understand it, those circuitry in Simscape. It wasn't particularly prepared for modeling such circuitry, but well, the quite great advantage of Simscape and MATLAB itself is a very well operating graphing tool. So you can quite easily get proper X, Y axis scaled and so on with quite visible results. Later on, we moved to LTSpice. Sorry, I just want to say that I hate drawing in LTSpice. It's like complete disaster. I don't know who sorry guys, but really, sorry, I don't know. Even yeah, even here, I was preparing it yesterday because I left my project on a separate computer, and I forgot what's the shortcut for rotating the element. So I decided after 5 minutes, I won't Google it. I will leave this diode like that and simply connect it because I have no power to use it. So okay, but generally, we compared. We did the same circuitry in LTSpice with a lot of sweat on that, but we got some results. It's a different, simpler, just to show how the simulator works in LTSpice. And last but not least, we did it in KiCad. Colors and so on, and R to rotate. After a few uses, we decided to stay with that. Not only because of the easiness to design circuits, but also due to the fact that we were able to simulate them. Okay. So I said a few good words about KiCad, but I have to say that before KiCad 8.0, the simulator graphic user interface for ngSpice was quite problematic, to be honest. Maybe it's connected to what yesterday was taught, that this graphic user interface is still under a huge need of improvement. But results were really nice, but operating on them was quite problematic. But then the KiCad 8 came up. I don't know what has changed, but it changed a lot. It simply made me able to get the results in a scaling that I'm hoping for, and I do not have to use stronger glasses to reach the results. So yeah, that was a huge improvement. But getting maybe quite fast to the ending of this presentation, the most important part here are those three almost the same graphs. Those are the results of simulations exported to a CSV file and let's say provided in the same form using MATLAB to compare if the results are close to each other. And no shock, they are. So why to use something pricey if you can get the same for free? So that was our outcomes of our research. So we are quite happy that we can use tools such KiCad and ngSpice. Even that originally, it's maybe not exactly what was the purpose of those tools. But if you are brave enough, you can use such tools for your needs. And this is what we did. Of course, I couldn't leave that space without maybe some requests or kind questions for further development to be considered. I was quite happy yesterday to hear that generally works around RF stuff in ngSpice are going on. I think that the RF part is quite important and getting more and more popular around. So generally, the area of RF simulations and RF design seems to be quite promising way to develop into the software. At least we will be very happy to have that, because one of the things that we are right now struggling with is, as I said, there are a lot of parameters and conditions that influence the results, because we have just a small amount of energy available. Really amount. It's the signal that is that we have on the receiving antenna is around -20, -30 dBms. So it's just a little energy, and in fact, every single change in humidity, temperature, whatever around us, the reflections influences what we get in the end. So we are right now working on the standardizing of the conditions of propagation, and the thing to be able to simulate also the RF path between transmitter and receiver would be a great deal to compare how those conditions impact the energy available on the RF energy harvester. Yeah, we are also wondering about the scripting simulations for batch processing, and it was also mentioned yesterday, because this step command for looping the simulations probably will be a little bit solving that, because, for example, we want to change parameter of LC component to look for resonance between the antenna and the rectifier. Requires simply comparing the values of particular elements. And of course, just a minor thing that I got the info from my friends. It's just sometimes the layout of the plotted graph is quite difficult to adjust. So the legend, for example, gets somewhere in the graph itself. So, but those are just minor things comparing to the fact that we get reliable results, which is really important for us when coping with such small energies and such high frequencies, because here I showed you the results for frequencies around 344 and 868 megahertz, but further on, the next step is Wi-Fi spectrum, so 2.4 gigahertz, and for the 5G, FR2, so simply the new radio standalone frequency range 2 areas, for example, being hopefully soon deployed in highly urbanized area, is 24 gigahertz. So we are going up. And just maybe a interesting fact, the first initial standard for 6G says that for some particular uses, there must be a need to use the frequency of up to 300 terahertz. I don't know why and how they want to achieve it, but well, maybe one day you will be able to look what your friend is watching on the TV using the, you know, thermal glasses to see the transmission back then. So yeah, a little bit earlier than scheduled, but thank you very much, and if there are any questions, feel free to raise them.
I have one. Well, thank you for your slides. I think a 6G forum is very ambitious. They just reinvented a TV remote, which is a communication device running at roughly 300 terahertz, if I did the math in my head correctly. But I'm more interested in if you have any ideas about synchronous rectification in a power harvesting device, because I imagine the voltage you get from the antenna at minuscule power is like 50 millivolts, maybe 0.1 volt. This is a high frequency signal. You need to somehow rectify it with minimal losses. You know, even super low bandgap semiconductors, they would, like germanium, they would get you 0.2 volt loss. So this merits a synchronous rectifier. Do you have any ideas how to implement one?
Well, there are different approaches how to solve this issue. One, of course, the original one was those Schottky diodes, but they are unable to cope with such low voltages. But there are also right now the architectures based on CMOS, and for example, differential drive coupling conductors that seem to be quite promising in achieving the goal for wideband also solutions.
Okay, maybe let's move this discussion outside the presentation, okay?
Thanks.
I just wanted to ask, have you made a bug report on those improvements?
About what? Sorry?
I said, have you made a bug report in the tracker for the features you wanted?
No, we haven't considered it as a bug, but as a... And you know, yeah, it's not a bug, it's a feature. Yeah, exactly. But maybe that's the thing that we can think of. So requesting such a new functionality in future releases. Good idea. Thanks.
Maybe again a little bit technical, but are you sure that the models for all the devices you're using are defined up to that frequency? Are you sure the models are defined up to that frequency you're using, or you're thinking of like?
Well, some of the designs we are taking from the literature to compare, because as I mentioned, we are right now working on the standardizing of the measurement and simulating environments, because there are a lot of architectures and topologies available, and the researchers tend to provide the best achieved efficiency, for example, but they are for different frequencies in different conditions. Some of them use real wireless transfer. Some of them use coax cables to connect transmitter and receiver. So we are right now proposing to unify the way you provide the results. And one of the next steps is to take a few of the designs already available and simulate them under the same conditions to verify if the results provided by the researchers are really the same in our environment. Of course, we are quite at the beginning of the research, but we are in the future hoping to propose maybe not entirely new design, but we tend to focus on the rectifier itself. This is why we are looking for those resonance and around this energy management after the antenna and before reaching the rest of the circuitry.
So one last question. It seems like you might be able to find more sources if you were tuned to 50 hertz in harmonics. Is there a reason other than antenna size that you're focusing on the higher frequency communication devices?
Well, generally, the devices that we want to power up are the close to zero or so-called zero energy sensors. So they are generally by standard quite small. So we need to be also as small as them to power them up.
All right. Thank you. Thank you, Jakub.
Thanks a lot once again.